We move now to memory virtualization. So let's look a bit more in detail at what happens when we want to virtualize the memory. Now, we discussed virtual memory and paging. So you know that the operating system, let's forget about virtualization for a moment. You know that when we have virtual memory, the operating system collaborating with the hardware, it's sort of lying to the processes thanks to the fact that it completely decouples the logical view from the physical view. And it not only lets each process believe it has a sequential set of addresses from 0 to something, but the important thing here is that it actually make the processes believe that the memory they have access to is actually larger than the physical memory you really have in your computer, because you are not really loading all the processes in their entirety, and even if you don't have free frames to load new parts of a process, you can still reclaim frames either from the same process or another process, as we discussed. So you separate this thing, the physical memory from the logical representation of it, what the process thinks is happening in the memory. Now you want to keep using virtual memory also if you run an hypervisor, because it's a very convenient and efficient, and it provides a lot of benefits. It's a technique that is efficient and provides benefits to handle the memory. Now you probably can agree with me that nonetheless, you cannot really play this game if you have multiple operating systems at the same time. Or at least you cannot play it without extra care, because you need to make each operating system believe it has access to the memory, while it not necessarily has the real mapping it thinks it has in the physical one. So basically, it's like playing the game of virtual memory, but now not between the physical memory and the processes, but now between the physical memory and the guest operating systems, which in turn will play the same game between their operating systems, the guest operating system, and their processes, okay? So what I'm trying to say is that if you run two virtual machines, and these ones use virtual memory, and they are trying to run two processes like this, each one will have its page table, and each one is allowed to use the page table to make the process believe the pages are in memory, even if in fact only some of them might be in the physical memory, and the mapping could be arbitrary depending on how you are filling in stuff in the page table. But you cannot do something like the thing that is shown in this figure, because you cannot make the two processes from two different operating systems believe that their page 0 is actually in frame 1, where frame 1 is the real frame 1 in the real hardware, because then of course you are using the same frame for two different operating systems, two different processes, and that is not going to work. So what you do is, probably you can imagine what is going to happen is that you add an extra layer in between, so that the hypervisor manages the operating system view of the memory, and then the operating system manages its own view of the memory when it comes to interacting with the processes, okay? And what you do is that you basically introduce a new page table, and this is called the shadow page table, that is maintained by the hypervisor, and this is used to translate what each virtual machine guest operating system sees as a frame into the actually real physical frame. It is nonetheless challenging to do this. The challenges are similar in spirit to the ones you have when you define virtual memory, but now again you have an extra layer, you have two layers at the same time that you need to take care of. You need to keep the page table at the operating system, at the guest operating system, and the shadow page table at the hypervisor synchronized. They need to be the same, because if the hypervisor thinks something and the guest operating system thinks something else, of course, that will eventually end up in problems, because the guest operating system will try to access memory that does not really belong, and not necessarily belong to that process or even to that entire guest operating system. The problem is, how do you keep them in sync? Because the guest operating system can keep updating its own page tables by just writing to memory, and the instruction it's using are not necessarily privileged or sensitive, so they don't necessarily trap the hypervisor. So how do you deal with this? You can go two ways here. You can be proactive. So when you see that the operating system is starting to create page tables, that is done with a privilege instruction, the hypervisor can keep track of where, in which part of the memory that is given to that operating system. The operating system is going to maintain the page table, mark those as read-only from the perspective of the hypervisor, of course, so that whenever the operating system tries to modify a page table, you will have, as a reaction, an interrupt that will wake up the hypervisor, and the hypervisor knows that at that point there is a change being made in the page table, and it can accordingly update the shadow page table. The other alternative is to be lazy and let the operating system do, the guest operating system do whatever it wants, because we know that at the end of the day, as soon as the operating system actually tries to access a frame that does not contain the page it wants, then there will be an interrupt. So the hypervisor will have a chance to synchronize the tables. The problem here is that being lazy does not solve all the problems. Specifically, it does not solve the problem of having the guest operating system removing some mappings from the page table, because in that case, since it's removing them, there will not be a page fault when it's trying to access them. And that can lead to situations in which the hypervisor has stale shadow page tables and believes the operating system, the guest operating system, is using more memory than it is actually using, because it does not see a change in the guest operating system page table. Now, here we need to differentiate now page faults. We have at this point two categories of page faults. We have guest-induced page faults and hypervisor-induced page faults. The guest-induced page fault is a page fault that will be intercepted by the hypervisor, for example, to update the shadow page table, as we just said. But these are actually page faults that the guest operating system needs to see, because these are the normal page faults you would have with virtual memory. So the hypervisor then needs to re-inject the page fault into the guest operating system, so that the guest operating system can take the actions that it is programmed to take. Then we have hypervisor-induced page faults. For example, if you make the memory used by the guest operating system to keep the page tables read-only, that are only intended for the hypervisor, again, to update the shadow page table, for example, but they don't need to be re-injected into the guest operating system. Okay, we say we are observing a VM exit, a virtual machine exit, whenever a page fault results in the hypervisor gaining control. Now we still have one complication here when it comes to virtualizing memory. So forget about virtualization for a moment. Virtual memory on a normal operating system, as I said, lies to the processes, makes them believe that they have more memory they actually physically have. And now back to virtualization, this happens also when the hypervisor lies to the guest operating systems, pretending they have more frames that are actually available. The problem now is, what if the hypervisor needs to reclaim some of the frames that they assign to a certain operating system because another operating system needs more frames? How can it do that? It's similar to what you need to do when you need to move frames from one process to the other, the problem is that now you don't have an operating system that sees the hardware directly and can take decisions. You have an hypervisor, and the hypervisor needs to be waken up by the guest operating system. The problem is that the hypervisor needs frames, but the guest operating system does not need to release frames. So how can we make the hypervisor tell the operating system, look, I need frames because some of them needs to be moved to a different guest operating system. Of course, you cannot take them simply away, because then you can disrupt the memory of the guest operating system. So a trick you can play here, it's called ballooning. So you can load a small module in each virtual machine as a pseudo device. It's not a real device, but it's a pseudo device driver, okay, that is connected to the hypervisor. So by doing this, you create a communication channel between the hypervisor and each guest operating system. Now, since the hypervisor has control of this, it can inflate, based on its own needs, the amount of memory it thinks it makes the operating system, the guest operating system believes it needs for the driver, okay? By doing this, it will assign more frames to the operating system, but it will be in control of those frames because they belong to this pseudo device driver that is controlled by the hypervisor. When the hypervisor needs frames, then it can deflate the memory needed by the driver. Since it deflates the memory, then the guest operating system will react by releasing the frames, and the hypervisor can intercept these frames and allocate them to a different guest operating system.